All right, so some useful tools. So basically what we are doing now is a little bit of what we call circuit analysis. So we will go into actually measure some things and also calculate some things. And the next tools are really handful, they are useful, not handful. There are also a handful, a few things that actually help you on making measurements and understanding how the electronics work. Okay, so first one is the a idea of equivalent resistance, and first of those is the series resistors. So if we have two resistors in series, meaning cascaded connection, the same current flowing through all, both of them, then sorry, then basically if you want to know what is the total resistance, meaning that what is the corresponding resistance that you can actually handle both of these. So basically the same current, meaning that the voltage potential drop over the first resistor and then voltage potential drop over the second resistor. They are here. So this is U1, U2, same as here, R1 times the current, and then R2 times the current is the voltage potential drop over the second one. And the total voltage is sum of those. And if we have the equivalent resistor R, it's a single resistor, then basically that resistance would be R1 plus R2. So if you have two resistors in series, then you have actually the same as the total resistance. This is quite handy. So if you don't have 2 kilo ohm resistor, but you have 1 kilo resistors, you just put those in series and now you have 2 kilo resistor. Easy. You might actually sometimes need that one. Or actually this works also as a voltage divider. If you want to know what is the voltage over one resistor when you have measured the total and the voltage and the current, you know that R1, then you can actually calculate this voltage over the first resistor, for example, and it comes up as a total voltage times the R1 portion of the total resistance, meaning that's okay. There's supposed to be a little space here, so anyways, the total voltage times R1 divided by R1 plus U2, R2. Okay, so simple. It's also a voltage divider. And equivalent resistor. The second equivalent resistance would be the parallel resistors, when we have two resistors in parallel. Okay, I have a dot missing here. It should have the current junction here. Then basically we have the same voltage over both resistors, and we have combined current. So current doesn't disappear. So if we have a current flowing through on a closed circuit, so then basically you are having the same current from flowing from the positive terminal and returning to the negative terminal. Okay, there's a so-called vikavirtasuodin or vikavirtakytkin, meaning it's a fault current detector, safety feature on household AC current. So basically, if some current is missing from the loop, then the circuit breaker goes off automatically to prevent any damage, since that current is flowing somewhere outside of that current loop. So yeah, one example of the current doesn't go anywhere. So two resistors in parallel. So we have current I1 flowing through the R1, and I2 is flowing through the R2. And the total current is basically just the sum of those two. We actually are already applying some of the laws that I didn't tell you, but anyways, just take my word this far. But what ends up is that it's a little bit, say, awkward to handle these kind of things. So it has these resistors basically are so basically the conductances are summable in this parallel resistor system. So 1 over R equals 1 over R1 plus 1 over R2. This could be also sometimes becomes handy. Since, well, these parallel resistor connections you have a lot. So basically there the R would be R1, R2 divided by R1 plus R2. Okay. This also works as a current divider. Okay, here we have the I1, I2. And using the Ohm's law, basically we can find that this I1 is actually proportional to R2 divided by the sum of the resistors. And likewise the I2 is proportional to R1 divided by the sum of the resistors. That's because basically we are talking about conductances. So the current flows through more on, so current finds the easiest way. So lower resistance means more current. Okay, so that also could come handy sometimes. So series resistors, you just add the resistors. You can use that one as a voltage divider. If you have parallel resistors, you actually inversely add the resistors, and you can use that as a current divider. And now we can take our first circuit analysis example, solving that U2 voltage over the R2 when basically that this voltage supply is known and those resistor values are known. By the way, when we have any these kind of pictures, circuit diagrams, whatever is marked on that circuit diagram initially, those are considered known variables, known parameters. Okay, so using the equivalent resistors, we can simplify this circuit. Okay, you can see, here we have a parallel resistors, R1 and R2. They basically are connected on between these points the same way. So the parallel resistance there R par is R1 times R3 divided by R1 plus R3. So basically next we can have this kind of equivalent circuit. So we have that R1 and R3 are now the simplified by one single resistor, and now you can use voltage divider equation to calculate the U2, which is simply the original the power supply voltage U times that resistor divided by R2 plus R par. Okay. So this way you can actually start analyzing circuits which has resistors or resistors in series or parallel. Okay, then we can also continue from that one to solve the current I. What is the total current? We can use here Ohm's law, U equals R times I. And we have the same. I is actually flowing through that R par and R2. So we can actually use this. Now we know the U2. We can actually use that one to calculate what is the current flowing through this component. We don't need to go and also take into account that one. We can actually simply take it from that resistor. And then use the current divider equation if we want to calculate this I1 and I3. Current divider R1, R3. So basically we have the current. Let's see, do I have the formula here? But no, you just use the current divider from did I lose everyone? I see white blank screen. Do you see anything than blank screen? Anyone?
Can you repeat the question?
I have a monitor window here which shows the blank screen now. Is it really blank screen what you are looking at, or are you looking at circuit analysis?
It is not. We are seeing the circuit analysis example.
Excellent,
number 4.
Excellent. So it's just, yeah, it's my Zoom meeting is now stalling. Oh, great. Okay.
Reboot.
No, I'm not touching as long as you see everything okay.
Can you try moving your mouse just to double check, because we are in slide 31.
Does it move?
It does not. It's frozen.
Okay. Does it say part 4 use current divider equation?
It does, yes.
Okay. We are on the same slide. Let's check from the next one. Okay. Did you get the Thevenin's theorem?
We did not know. It's frozen.
It's frozen. It's frozen again.
Have you tried resetting your monitor or your mouse?
Okay, let me check this
one. I'm joking. I'm joking.
Let me check this. Zoom meeting. I don't get it. Okay. At least I got my Thevenin's theorem back. Did you?
No, unfortunately.
That's very strange. So I should be seeing whatever you are seeing here. Come on.
Perhaps if you repeat the previous step of just stop streaming in Zoom and restream it and see if that
Yeah, the problem is
solves
that problem is that I don't have any access to the display now. Oh, great.
Oh, okay, fair enough.
Yeah. So it's really stalling, not responding. The Zoom meeting window is not responding at all.
Control-Alt-Delete. Try to see if that opens Task Manager.
Yeah. No, it doesn't.
Check your... Do you use dual monitors?
Let me try to log out. It worked last time pretty well, right?
It did, yes.